Hello cosmic adventurers, and welcome back to What Is, the channel where we try to demystify the universe one monumental question at a time. Today we're plunging into one of the most profound and perplexing mysteries of modern science, a riddle wrapped in an enigma, cloaked in, well, darkness. We're talking, of course, about dark matter. It's a term you probably heard, whispered in documentaries, headline articles, or perhaps while overhearing a particularly intense conversation at a science museum. But what is dark matter? Is it a cosmic boogeyman, an invisible space monster, or just physics' way of saying we've found something really weird and we need a cool name for it? Strap in because we're about to explore the invisible scaffolding of the universe, trace the origins of a revolutionary theory, marvel at the ingenious ways scientists are trying to prove its existence, and peer into the future that might just redefine everything we thought we knew about reality. So let's start with the big question, the one that kicks off every episode. What is dark matter? At its simplest, dark matter is the universe's invisible majority. It's a hypothetical form of matter that, unlike the stuff you, me, and everything you can see are made of, doesn't interact with light or other forms of electromagnetic radiation. That means it doesn't absorb, reflect, or emit light. It's utterly, perfectly, magnificently transparent. And because light is how we see everything in the universe, from distant galaxies to the dust motes dancing in a sunbeam, not interacting with light makes dark matter incredibly difficult to detect directly. It's essentially invisible. Now, before you go thinking it's some kind of cosmic ninja, let's be clear about what dark really means here. It doesn't mean literally dark in color, like a black hole. It means it's electromagnetically dark. It just doesn't play nicely with photons. It doesn't glow, it doesn't shimmer, it doesn't even cast a shadow when you see it. It's the ultimate wallflower at the cosmic dance, present but utterly unnoticeable through conventional means. However, just because it doesn't interact with light doesn't mean it doesn't interact at all. We believe it does interact through gravity. And it's this gravitational influence, this invisible hand tugging at the luminous matter we can see, that gave us the first hint that something was amiss in our cosmic accounting books. We can't see it, but we can see its effects. It's like hearing a strange rustling in the bushes. You can't see the creature, but you know something's there because the leaves are moving. Dark matter is the creature rustling the cosmic leaves. For decades, the standard model of cosmology, what we call the lambda CDM model, has dictated that visible, or baryonic matter, everything from stardust to superstars, makes up only about 5% of the universe's total mass energy content. About 68% is taken up by dark energy, an even more mysterious force driving the accelerating expansion of the universe. And the remaining 27%? That's our elusive friend, dark matter. Think about that. Everything you've ever seen, touched, or even dreamed of is just a tiny fraction of what's truly out there. Dark matter is the silent, unseen scaffolding upon which the visible universe hangs. But how did we even come up with such a wild idea? Surely scientists didn't just wake up one morning and say, you know what? Let's invent an invisible substance to explain things. Well, not quite. The origin of dark matter theory is a story of unexpected observations, stubborn data, a dash of brilliant, if sometimes cantankerous, scientific intuition. Our story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Now, Zwicky was a character. He was known for his brilliant mind, his sharp wit, and his equally sharp tongue. He famously called his colleagues spherical bastards, claiming they were only bastards no matter which way you looked at them. Not exactly a team player, but undeniably a visionary. Zwicky was observing the Coma Cluster, a massive collection of thousands of galaxies, about 300 million light-years away. He was trying to measure the velocities of these galaxies, how fast they were moving. He used the Doppler effect, observing how much light from distant galaxies was either red-shifted, moving away, or blue-shifted, moving towards us, to calculate their speeds. What he found was baffling. The galaxies in the Coma Cluster were moving far too fast to remain bound together by gravitational pull of the visible matter alone. According to his calculations, the cluster should have flown apart eons ago. It was like watching a carousel spinning so fast that all the horses should have been flung into the next county, yet somehow they remained perfectly attached. There had to be an immense amount of unseen mass providing the extra gravitational glue to hold the cluster together. Zwicky estimated that there must be about 400 times more mass than what he could account for with the visible galaxies. He coined the term Dunkel Materia, or dark matter, to describe this missing mass. His findings, while intriguing, were largely ignored for decades. Perhaps it was his abrasive personality, or perhaps the idea was just too radical for the time. But the universe, it turns out, is a very stubborn place, and inconvenient truths have a habit of resurfacing. Fast forward to the 1970s, and enter another brilliant astronomer, Vera Rubin. Unlike Zwicky, Rubin was meticulous, patient, and less prone to calling people spherical bastards. She and her colleague Kent Ford were studying the rotational curves of spiral galaxies, specifically the Andromeda galaxy. Imagine our solar system. Mercury orbits the Sun faster than Earth, which orbits faster than Jupiter, and so on. This is because the vast majority of the mass in our solar system is concentrated at the center, in the Sun. Planets further out experience less gravitational pull and thus move slower. This is how we'd expect stars in a galaxy to behave too. We'd expect stars closer to the galactic center to orbit faster, and stars further out, where less visible mass is contained within their orbit, to slow down. But Vera Rubin found something astonishingly different. When she plotted the orbital speeds of stars against their distance from the galactic center, she expected to see speeds drop off significantly at the outer edges of the galaxy. Instead, she found that speeds remained stubbornly, almost infuriatingly flat. Stars far out from the galactic center were moving just as fast, or even faster, than stars close in. It was like watching a merry-go-round where the horses on the outer edge were spinning at the same speeds as the horses in the center. Which, if you know anything about physics, means that the outer horses should have been flung off into space due to centripetal forces. But they weren't. They were staying put. The only explanation was there must be a huge, invisible halo of mass surrounding the galaxy, extending far beyond the visible stars, providing the extra gravitational pull needed to keep those outer stars in their rapid orbits. Rubin's work provided compelling, undeniable evidence for the existence of this unseen mass. Her observations, confirmed through countless studies of other galaxies, brought Zwicky's dark matter theory from the fringes of eccentricity right into the scientific mainstream. It was no longer just a weird idea. It was a necessary component to make the universe behave according to the laws of physics as we understood them. So the theory was born out of gravitational anomalies. But how has it developed since then? And what further proof, or at least what overwhelming evidence, have we gathered? The development of dark matter theory has been the story of increasingly sophisticated telescopic observations, cosmic detective work, and some truly mind-bending physics. One of the most powerful tools in this arsenal has been the study of cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, the oldest light in the universe. It's a snapshot of the universe when it was just 380,000 years old, a mere baby in cosmic terms. By meticulously mapping tiny temperature fluctuations in this background radiation, missions like COBE, WMAP, and the Planck satellite have given us an incredibly precise cosmic census. And what did that census reveal? That dark matter isn't just a local galactic quirk. It's a fundamental constituent of the entire universe. Those tiny fluctuations, the seeds of all future cosmic structures, could only have formed and evolved into the galaxies and galaxy clusters we see today if dark matter was present in precisely the quantities we now describe. Without it, the universe would look very different, much smoother, and far less interesting. Another powerful piece of evidence comes from the phenomenon known as gravitational lensing. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time, and light, following these warps, appears to bend around them. This is gravitational lensing. When we observe distant galaxies through closer, massive galaxy clusters, the light from background galaxies gets distorted, stretched, or even multiplied into multiple images, just like looking through a distorted glass. By carefully analyzing these lensing effects, astronomers can map the distribution of mass in the foreground cluster. Time and time again, what they find is that the mass distribution inferred from the lensing far exceeds the mass visible in the stars and gas. The lens is much heavier than it appears. This invisible mass, once again, aligns perfectly with the predictions of dark matter. It's like seeing tire tracks in the mud, but no car. You know something heavy passed through, even though it's invisible to you. Perhaps the most compelling smoking gun evidence for dark matter comes from a cosmic collision known as the Bullet Cluster. This is a truly spectacular event. Two galaxy clusters that have smashed right through each other and kept going. When scientists studied the Bullet Cluster, they made a fascinating discovery. The hot gas, which makes up most of the visible mass in the cluster, has been slowed down and heated by friction during the collision, creating a distinct bullet-shaped shockwave. But the overall mass is mapped by gravitational lensing and has sailed right through the collision, largely unaffected. This is critical. If dark matter was just ordinary matter that wasn't shining, it would have behaved like the hot gas, slowing down and interacting. But it didn't. It passed right through itself and the ordinary matter, almost as if it wasn't there. This provided direct evidence that dark matter was not just dark gas or dark dust, it was something fundamentally different. Something that interacts primarily through gravity, but hardly at all through the strong, weak, or electromagnetic forces that govern ordinary matter. It's the ultimate cosmic ghost, passing through everything. So if dark matter is not visible matter, what is it? This is where the theoretical physicists step up. Armed with chalkboards, supercomputers, and an endless supply of caffeine. Over the years, many candidates have been proposed, some more exotic than others. Early theories suggested that dark matter might be composed of machos, massive astrophysical compact halo objects. These would be things like black holes, neutron stars, brown dwarfs, that's a failed star, or white dwarfs. Essentially very dim or dark astronomical bodies made of ordinary matter. However, extensive surveys using gravitational microlensing, looking for slight brightening of background stars as machos pass in front of them, have largely ruled out machos as accounting for a significant portion of dark matter. There simply aren't enough of them, and their existence would have other observable effects that we don't see. This leaves us with the more exotic non-baryonic candidates. The leading contender for decades has been WIMPs, weakly interacting massive particles. WIMPs are hypothetical particles that would be much heavier than a proton, interact via the weak nuclear force and gravity, but not electromagnetically or strongly. They would be slow-moving or cold, which fits with the formation of large-scale structures we observe. Many particle physics theories, like supersymmetry, naturally predict the existence of such particles. Imagine a whole zoo of particles we haven't discovered yet, all around us, passing right through us all the time. It's humbling, if not a little creepy. Other candidates include axions, which are much lighter than WIMPs and were originally proposed to solve a different problem in particle physics, but could also contribute to dark matter. Or sterile neutrinos, which could be a type of neutrino that interacts even less than the already famous elusive regular neutrinos. The list is long, and frankly, some of these particles sound like they were invented by a particularly creative Dungeons & Dragons dungeon master. So with all this compelling indirect evidence, have we found any direct proof of dark matter's existence? And if not, what are we doing to find it? The answer to the first question is, frustratingly, no, not yet. We have no definitive, unambiguous direct detection of dark matter particles, but that doesn't mean scientists aren't trying, and the effort involved is monumental. Imagine trying to catch a ghost made of, say, silence. That's essentially the challenge. Because dark matter interacts so weakly, detecting it requires extreme sensitivity and isolation. Scientists have built huge, elaborate experiments deep underground, shielded from cosmic rays and all other known particles, hoping to catch a rare, fleeting interaction between a dark matter particle and an atomic nucleus. These underground labs, located in abandoned mines or specially dug caverns, has detectors filled with supercooled liquefied gases, like xenon or argon. The idea is that if a WIMP, for instance, passes through the detector and occasionally collides with an atomic nucleus, it would cause a tiny recoil, producing a faint flash of light or a whisper of ionization. It's like trying to hear a feather drop in a completely soundproofed room. Experiments like Xenon, Lux, LZ, and Panda X, and many others, are pushing the boundaries of detection technology, searching for these incredibly rare events. So far, they've set impressive limits on what dark matter isn't, ruling out certain masses and interaction strengths, but no definitive ping has sounded the alarm. Another avenue of direct detection involves looking for the byproducts of dark matter annihilation. If WIMPs are their own antiparticles, they might occasionally collide and annihilate, producing gamma rays or other particles we can detect. Space telescopes like the Fermi Gamma Ray Space Telescope scan the cosmos for these telltale signatures, particularly from regions rich in dark matter, like the galactic center. Again, hints have emerged, but nothing conclusive enough to declare victory. And then there's the possibility that our particle accelerators, like the Large Hadron Collider at CERN, could create dark matter particles in high energy collisions. If supersymmetry is correct, for example, then the supersymmetric partners of known particles, including potential WIMPs, might be detectable. The LHC has proved a powerful tool for discovering new particles, including the Higgs boson, but dark matter particles have so far remained frustratingly out of reach in these terrestrial experiments. The incredible thing is that despite decades of searching, despite billions of dollars and countless hours of brilliant scientific minds, we've found nothing definitive. And paradoxically, that lack of direct detection is almost as interesting as the discovery would be. It means dark matter is even more elusive than we thought, forcing theoretical physicists back to their chalkboards to revise models and propose even stranger, more weakly interacting particles. The universe, it seems, enjoys a good game of hide and seek. So what does the future hold for the quest for dark matter? The search certainly isn't slowing down. Next generation direct detection experiments are being designed, aiming for even greater sensitivity. The LHC and future particle accelerators will continue to probe higher energies, hoping to unlock new realms of physics where dark matter particles might reside. New telescopes and observatories, both on Earth and in space, will continue to map the universe with increasing precision, refining our understanding of dark matter's distribution and gravitational effects. There's also a category of alternative theories that challenge the very premise of dark matter. The most prominent of these is modified Newtonian dynamics, or MOND. MOND proposes it at very low accelerations, like those experienced by stars in the outer reaches of galaxies. Gravity behaves differently than predicted by Newton and Einstein. Instead of inventing a new particle, MOND modifies the laws of gravity themselves. While MOND can explain why a galaxy rotation curves remarkably well in some cases, it struggles to explain other phenomena, like gravitational lensing in galaxy clusters or the bullet cluster, and particularly the cosmic microwave background. The prevailing scientific consensus still favors dark matter because it offers a more consistent explanation for a wider range of cosmological observations. But the fact that MOND exists and has its proponents shows that the scientific community is open to truly radical solutions if the evidence eventually demands it. Ultimately, the discovery of dark matter or a comprehensive understanding of what it is would mark a monumental shift in our understanding of the universe. It would not only reveal a huge, previously unknown component of reality, but could also lead to new physics beyond the standard model of particle physics. It could connect the largest structures in the cosmos with the smallest particles. It might even offer clues about the early universe, the nature of space-time, or the very fabric of existence. Imagine a universe where 95% of everything is fundamentally different from the 5% we experience. That's the universe we're trying to understand. The quest for dark matter is a testament to human curiosity, perseverance, and the relentless drive to uncover the deepest secrets of reality, even when those secrets are incredibly, frustratingly dark. Whether it's a WIMP, an axion, a sterile neutrino, or something we haven't even conceived of yet, one thing is certain: dark matter is out there. It's tugging at the stars, shaping the galaxies, and forming the invisible backbone of the cosmos. And someday, perhaps with a flash of light in a deep underground lab, or a subtle anomaly in a particle collider, or a revolutionary insight from a new theory, we might just finally drag this cosmic ghost into the light. And when we do, our universe will never look the same again. So what do you think dark matter is? Do you have a favorite hypothetical particle? Or do you think there's a different explanation altogether? Let us know in the comments below. If you enjoyed this cosmic deep dive, please remember to hit that like button, share this video with your fellow curious minds, and subscribe to What Is for more explorations into the universe's most mind-bending questions. And don't forget to ring that notification bell so you don't miss our next adventure. Thanks for watching, and as always, keep wondering. See you next time.